Hello everyone. In this section, we're gonna learn about the indefinite integral, indefinite integral, uh, indefinite integral. Actually, we learned about the indefinite integral earlier, but even though we didn't use the name, for example, you remember antiderivatives, derivatives. So those are the indefinite integrals. So it's just a new name. Okay? Just a new name. So antiderivatives we call indefinite integrals. Okay. So let's recall some facts that we learned in the previous section. Remember, in the fundamental theorem of calculus, we learned two things. So we have the fundamental theorem of calculus. So we talk about the first thing. What we talk about is if the first one, if is continuous, if f is continuous, then we say that the derivative of the integral fx dx equal fx. So right. So what does that mean? That means because that means so this follows that means a to fx dx is an antiderivative, right? Because once you take the derivative, you get the function back. So that means this is an antiderivative of you can say of f. Okay, it's an antiderivative of f. That's the first result says. What's the second result says? So the second result says a to, we can say a to b fx dx is simply equal to f b minus f a, where f is any any antiderivative, any derivative. Okay, so those are the two results we learned in the previous section. So now what we need is just a notation. So what we're trying to do, and also I'm going to put few things here before, like for example, the third one that I want to recall is the area. So so we learned that a to b fx dx is the area below the curve. So right, below the curve y equal fx, and the x-axis if the function f is positive or 0, but normally that doesn't happen always. So in general, the actual area is a to b absolute value of fx dx. So if you need to find the area, make sure that the function is positive, otherwise you don't get the area here. Okay, is the area in general. Okay, in general, that's the area in general, because this even works for a function which has part positive, part negative. Because if you take the absolute value, you always get the positive side. So that means if you add them, you actually get the area when the function is negative. Okay, so that's so you have to take the absolute value to actually get the area. So this is the kind of summary of what we did earlier. Okay, so now what we want to do is we just need to find a notation for the antiderivative. So so let's talk about the notation there. So there's nothing new here. So you can see we just continue from the previous one. So the notation, okay, so notation for a what we call notation of the indefinite integral. Indefinite integral. The notation of the indefinite integral is simply just write fx dx. So we don't write the limit, we just write it like that. So this is equal to fx as before. Okay, So means that if you take the derivative of big F, you get the small f. Okay, so that's the kind of idea. So the so just the notation is this one. This is the notation for indefinite integral. Okay? Just write any antiderivative. So as examples, so we can say x squared dx, the indefinite integral of x squared dx is simply x3 over 3 plus c. Okay, since if you take the derivative of x3 plus 3 with any constant, you're gonna see that you're gonna get, what do you get? 3x squared over 3, which is x squared, right? So that's the reason. So make sure that this is, you add the c here, because even if you have any constant there, you still get the same answer. So c can be any constant. Okay, c is any constant. So c is an arbitrary, that's how we call it, arbitrary constant. Okay, or pretty much any constant, any number. Okay, so I mean, theory is over. So what we want to do is like do some examples. So I'm going to do one, I'm going to do one more here. So how about secant squared x dx? What do you want to think? We want to think about a function of which the derivative is x secant squared x. What is that function? You remember from calc 1, it is the function is the tan x. So you need to add the c again, since the derivative of the tan x plus c equal secant squared x. Okay, so things like that. So number 3. So what about 3 over x squared plus 4 dx? So this was in the table before. So you can write this one as 3 over x squared plus 2 squared. So then the 2 is the a here, so that means the answer was 3, you write, and so 1 over a, so 1 over 2, and then 1 over 2, and then what happened, it is tan inverse x over 2 plus c. Okay, that's the answer. This is coming from the table. Okay, this is coming from the table. Okay, let's just do one more. So so integral of say shin x, that's the hyperbolic sign. What is the integral of shin x, which is simply cos x plus c. So you can see that this is slightly different. In the regular case, if you have sin x, dx, we know that this is negative cosine x, right? So there's a difference between when you have the hyperbolic sine or cosine, that's positive. Okay, so that's one difference, but otherwise this hyperbolic sine cosine are really important. I'm just going to give the definition here, and then you can prove that that's the case. So we write the hyperbolic hyperbolic cosine, which is e to the x plus e to the minus x divided by 2. Okay, and the hyperbolic sine, shin, we call it shin, cos and shin, this is ex minus e to the minus x over 2. So that's the only difference between the two. And then you can see that if this is the case, if you take the derivative of one, you get the other one. If you take the derivative of one, you get the other one. For example, the derivative of cos x is, you can prove that it is simply sin x. Okay, so I'm gonna give you this as an exercise to prove. Okay, so consider this as an exercise. Okay, so I'll just prove them. Okay, so prove that derivative of cos is sin, derivative of sin is cos. Okay, just go back and forth. So that means it makes it easy. When you see the hyperbolic sine or cosine, it just whether the integral or derivative, the other one. Okay, but that doesn't work with the regular one, because when you take the derivative of cosine, it is negative sine, but that's not the case with the hyperbolic function. Okay, so those, at least those two are important, because for most of the engineering applications they use sin and cos. Okay, so so that's not actually in the syllabus, but we need to know that. Okay, so there's no excuse for that. So make sure that you understand, you remember the hyperbolic sine and hyperbolic cosine as part of the course. Okay, so okay, now what I'm going to give you, I'm going to give you like a little remember the table that we discussed before. So I'm going to like give like few very common ones here again, but make sure that you go back to the table that we discussed there, because that's like much more you know, important. And it has like the other one also had some equations that that we can prove later, because that's the major one. But I'm gonna like kind of repeat few things here just to help you for the homework. Okay, so let's try them quickly. I'm going to call it table of integrals. Table of integrals. This is just for the homework, but remember the other one. The other one is the more important one. So, so I'm going to write, you know, yeah. So we have a constant fx dx, which is c. You can take the constant out and then integrate fx dx. And then we had the sum formula. If you have a sum fx plus gx dx, which is simply integral of fx dx plus the integral of gx dx. Okay, so if you have a sum, you can split it. If you have minus, still you can split it. Okay, so plus or minus. So there are no product rule or quotient rule with integrals. No product rule, no quotient rule. Okay, I'm going to write it here. So no product or quotient rules. Okay, no product or quotient rules. We have a different one we're going to talk about later, called integration by parts. That's slightly related to the product rule. Okay, but there are no real product or quotient rules. Okay, and then we also had the k dx, if you have a constant, so which is kx plus c, and then we have two power rules. So we have 1 over no, not 1 over, let's write that one first. Let's write xn dx, which is x n plus 1 over n plus 1 plus c, n not equal to -1, and when n equal to -1, you get 1 over x dx, which we know as natural log x plus c. Okay, good. And then the exponential function ex dx, which is ex plus c. And then if you have any other base like bx, any other base, so what's going to happen, it is bx, but you have to divide by ln b. So that's the only difference. You have to divide by ln b, and we assume that b not equal to 1 here, or negative. Okay, so it has to be positive. Okay, that's ex. And then we have sin x dx and the cosine x dx. What is sin x dx? It is a negative cosine x dx. I'm sorry, not dx. Okay, negative cosine x plus c. And then this is sine x plus c, and then we have hyperbolic, so we have shin hyperbolic sine dx and hyperbolic cosine okay, so there's a we are missing x here, so hyperbolic sine x and the hyperbolic cosine x dx, but we know that they are all positive, so that's the difference. So it's a cos x plus c, this is shin x plus c. Okay, so they are all positive. Okay, and then we have the secant, we have secant squared x dx and the cosecant squared x dx. So secant, that is tan x plus c, so cosecant is a negative cotan x plus c. Okay, good. And then we have a secant tan, we have secant x tan x dx, and then we have cosecant x cotangent x dx. So what happened? I have the secant tan, which is secant x. If we have cosecant cotangent, it is negative cosecant x. Okay, and then we have just one more. We have 1 over x squared plus a squared dx, which is 1 over a tan inverse x over a plus c. Some people write this one as arctan. Okay, arctan x over a, so 1 over a. So yeah, but I don't write it much. Okay, and then we have 1 over a squared minus x squared square root dx, which is simply sine inverse. There's no 1 over here, x over a plus c. Okay, so those are the kind of most important one, or I should say most common ones, but there are a few more, and you can see the larger list in the other one, and the other formulas we're going to prove later. Okay, so for example, here we did not mention what is the secant x dx, so we don't know, right? So we don't know that. So we don't know what is the tan x dx. See, so we don't know that, but those things you can see in the table that I gave Monday. Okay, so remember that table, but we're gonna prove those things later, so you have to wait a few more days until after the first exam to learn about them. Okay, so you can see that this is complicated, so yeah, but we can discuss them later. Okay, good. So that's like kind of common table. So let's try to do some few more examples. The theory is over. Okay, so good. So so let's do a few more examples. Okay, good. So more examples. Okay, so find the general indefinite integral. We don't need we don't need the word, but just say exaggeration. So so let's say 10 x to the 4th minus 2 secant squared x dx. So so we can use a power rule here. For the first one we can use a power rule, so it is 10 x to the 5th over 5th minus 2 what is the secant squared? Actually, what I'm gonna do is I'm gonna like kind of write it because this is the first example. I'm gonna like kind of do all the steps, but you can skip some steps later. For example, if you have 2, you can split it. So how you do, you can take the constant out. So this is what's gonna happen actually. You can take the constant out, and then you're gonna integrate x to the 4 dx, because using the sum rule, minus you take 2 out and integrate secant squared x dx. That's the first step. This step actually you can ignore. So then you write your answer 10 x to the 5th over 5th minus 2 secant squared. Secant squared means 10x. Now you added only one c. You can add 2 c's, but you don't need, you just add 1 c, and then if possible you need to simplify. So if you simplify 2 x to the 5th minus 2 10x plus c, so that's the final answer. Okay, but you can skip, you can, if you can write this final answer directly from that, that's okay. So there's nothing wrong with that. Okay, so let's do another one. How about this one? Integral of cosine theta over sine squared theta. So there may be some integrals like that. You need to do some simplifications before you do that, because you can see there's no way you can figure out what's going on here. Okay, so the best thing would be do some trigonometric tricks, use some trigonometric tricks to simplify this first, to bring it to one of those formulas in the table. Okay, so what you can do is, what I'm going to do, I'm going to split this. You can write 1 over sine. I'm going to take one sine, and then I'm going to write the other sine with the cosine. So this is like kind of common trick here. So if I use that trick here, now what's going to happen, the first one going to give you cosecant theta, the second one going to give you cotangent theta. Now you can see that there is a formula like that in the table, and according to the table, this is simply going to be negative cosecant theta plus c. Okay, this just comes from the table. So you can see that if you use simple algebra, simple trigonometry tricks, you can simplify some integrals to something that that you can work with. Okay, so you have to bring it to this one. After that you can use a table. Okay, so it's not clearly like clear from the first one. You need to do the simplification first. Okay, so another one, how about this one? So this is like evaluate. Okay, we have to say evaluate. Evaluate means find the number, right? So it's 0 to 3 x to the 3 6x. Okay, something like that. But this is a definite integral. Okay, so if you have a definite integral, what we normally do is we first find the any antiderivative, and then you plug in the numbers, right? So we first find the antiderivative. So in this case, x to the 4 over 4 minus 6 times x squared over 2, that means 3x squared. Now you put the numbers there, so it is 3 and a 0. So let's plug in here. So if you plug in 3, it says 3 to the 4 over 4 minus 3 and then 3 squared, that's the first number, minus, when you plug in 0, everything is 0, so you don't want to do anything with that. So now you simplify, so you're gonna get 81 over 4 minus, how much you get, 27. So, and if you simplify this one, you're gonna get pretty good. So so you get, because if you multiply by 4, yeah, so you're gonna get negative 6.75. and in the homework, make sure that sometime when you put the decimal, it's not gonna accept. So please read the instructions what they need, whether they need the decimals or they need as a fraction. Okay, because that's where sometimes we get errors even though your answer is right. Okay, so that's about that. So let's do a few more examples. So maybe I'm gonna do like maybe 2 more. Yeah. Okay, so another one. D. How about this one? Find 0 to 2 2x3 minus 6x plus 3 over x squared plus 1. A lot of terms. That's okay. Good. So what's the answer? So what do we need to do? So 0 to 2x3 minus 6x plus 3 over x squared plus 1 dx. So find an antiderivative, so it's easy. So you're gonna get 2x4 over 4 minus 6 x squared over 2 plus 3 tan inverse x over 1, so tan inverse x. Okay, and then you're going to evaluate this at 2 and 0. So let's simplify this first, so you can see that this is x to the 4th over 2 minus 3x squared plus 3 tan inverse x. So if you plug in 2, so you get 2 squared, not 2 squared, 2 to the 4th over 2 minus 3 2 squared plus 3 tan inverse 2 minus first two terms you get 0. For the last one you get 3 tan inverse 0. How much tan inverse 0? Tan inverse 0 is 0, right? If you look at the tan graph, it's go like that. It's passed through 0. So even if you go the inverse, it's asymptote pi over 2. So if you look at the inverse, it's still 0. Okay, so it's gonna go away there. So what you get now is you get 16, so 8, and then minus 12, so it's get 4. No, you get like 16, so it's 8, so 8 minus 12, so negative 4. So you get 3 tan inverse 2 negative 4. Okay, so that's the final answer. 2 tan inverse 2 negative 4. So, and then when you do the homework, please check whether they need the exact value. If they need the exact value, this is what you want to enter. Sometimes the tan inverse they write as arctan. Okay, so it is arctan 2. So or sometimes they say, okay, leave to up to 2 decimal places correct, 3 decimal places correct. So please read them. Okay, so if you go with the decimals, so you're gonna get this is roughly negative 0.67855. That's an interesting number. Yeah, so if it's up to 2 decimal places, it's going to be 6.68. Up to 3 decimal places, it's going to be 679. So it's like that. Okay, so please read the information and to check what they're asking. Okay, so let's do one more example before we talk about some kind of applications. So this is the last one of this type. Let's say 1 to 9 2t squared plus t squared square root t minus 1 over t squared. This is interesting. Actually, we have done these kind of problems before. What you want to do, you want to split this first, you're going to divide first. Okay, so if you divide, so what do you get? So you're gonna get, this is 1 to 9. First you divide by t squared, so you're gonna get 2, and if you divide by t squared, you're gonna get square root t, and then minus 1 over t squared. Okay, so that's what you get first. Now you're gonna integrate term by term. So 2 gonna give you 2t, and then this one gonna give you t to the 3 halves divided by 3 halves, and this is 1 over t squared means t to the negative 2. So that means it is when you add 1 divided by that. So this is what you get, because you can write this one as t to the negative 2 first. You write this one as t to the negative 2 and then use the power rule. So power rule says that you add 1 and divided by that same number. Okay, so that's how you get there. Okay, now you're going to evaluate this at 9 and 1. So you plug in 9 first. So plug in 9, you're gonna get 2 times 9 plus 9 3/2 over 2/3 minus this is 1 over the plus sign. This is 1 over 9, right? And then minus, now you subtract, adding 1, so it's 2, and then this is become 2/3, and then this is so it's a 1, so it's a plus 1. That's what you get. And if you simplify this, you're gonna end up getting 32 4 over 9. Okay, that's the exact value. And again, look at the instruction in the web design just to check what they're asking, whether they're asking a number or whether they're asking a whether they're asking exact value, whether they're asking a approximation. Okay, good. And then I'm gonna kind of recall what we did earlier in the under the definite integrals. We talk about under the fundamental theorem of calculus, we talk about what we call the net change theorem. So I'm gonna repeat that again here. So what is the net change theorem? This is a repetition of what we did in the previous section. Okay, net change theorem. So what the net change theorem says is that if you integrate the rate of change or the derivative, you get the you get the net change. Okay, so the integral of the derivative. Okay, integral of the derivative. Derivative means what? Rate of change. Okay, rate of change. Integral of the derivative. Integral of the derivative is the net change. Okay, is the net change. So as a formula, it says that a to b, the derivative of a function is simply going to be the net change of the function. So remember, this has to be the derivative ab. Okay, so that is the net change formula. And then we discussed few examples also in the previous one, so I'm going to repeat one of them and do just one example here. So for example, so let's say how about so some examples. So the derivative is the velocity. Derivative is the velocity et, and the function is displacement. Okay, so the function is the displacement. So something like that. So that means you can write them as a b. If you integrate the velocity, so if you get the velocity, if you integrate that, then you're gonna get the displacement. Okay, and then if you integrate the absolute value of the velocity, in other words, if you integrate the speed, if you integrate the speed, this is a t, you end up getting total distance traveled. Actually, this one can be used for anything. So if you know the rate of change, okay, I'm sorry. So the displacement that we in this case, it can be if you say function or the displacement is like this, it's be s b minus sa, sb minus sa as a formula. So so what I'm going to tell you, so if you know the rate of change, then just integrate, you get the function difference. So right, so if you know the rate of change, you get the function difference. So you're gonna say t1, t2, whatever quantity, but you know the rate of change, and if you know the rate of change, you simply get the function difference here. Okay, so v1. So this is the simply the rate of change. This is simply the rate of change of v. So that's the rate of change of v. So it can be anything, any rate of change. Then it's gonna work like that. So what we need to do, if you know the rate of change, if you integrate that, you're gonna get the net change. Okay, that's what you call the net change theorem. So I'm going to like maybe one example. We did one example before in the previous section. So let's do one more example just to make sure that we kind of understand the idea. So and then that's going to be the end of this section. Okay, so I'm going to do just one example here. So let's say this one. So example is a particle moves along a line when you say line, is straight line, so that its velocity at time t is vt equal t squared minus t minus 6. Okay, and then this is meters per second. So they're asking the first part, find the displacement in the time period. So find the displacement in the time period from 1 to 4. Okay, from 1 to 4, and then ask find the total distance traveled. Find the distance traveled from during this time. Same time period. Okay, so this is like kind of very typical question. So you're gonna get a function like that, and then they're asking what's the displacement and what's the total distance traveled. When you say distance, remember it's related to the speed, so take the absolute value. Okay, so the answers, so let's see how it works. The answer for part A, we know that the displacement according to the net change theorem, the displacement is simply the it is s to the 4 minus s to the 1 in this case, but from the according to net change theorem, it is simply 1 to 4 the derivative. So right, 1 to 4 the derivative, but the derivative is simply the velocity in this case, so it's become vt. Now what we're trying to do is we're going to plug in there and integrate. So it is 1 to 4 t squared minus t minus 6 the integral. You can see that this is like very easy integral, very easy integral. So you're going to get t3 over 3 minus t squared over 2 minus 6t. So you're going to plug in 4 and 1. So if you plug in 4 and 1 and simplify, you should end up getting 9/2. Okay, so the 9/2 is a displacement. This is in meters. Okay, this is in meters. So so you can say it's negative. What does that mean? So it's go backward. So right, so you can say the particle moved 4.5 meters to the left. So if you say if you measure that, you're gonna go that way. So now what actually happen is it gonna move during in that 4 to 5 it moved to the left for 5 meters from the beginning of the time 1 second. Part B. So we need the absolute value. Why we need the absolute value? You can see that this function okay, what's really going on here? So let's say note that the velocity function vt, which is t squared minus t minus 6, what are the factors? The factors are t minus 3 and t plus 2, right? So now what happened? So that means if the t is smaller than 3, this is negative. If t is more than 3, this is positive. So that means note that, and the velocity, the vt, is negative or 0 on the interval 1 to 3, right? And the velocity is positive on you can say equal sign, okay, on the interval 3 to 4. See, that's what it notice because of the t minus 3 term. So you can see that there's a negative sign here. So that means if it is less than 3, it is negative. If it is more than 3, it is positive. Okay, so that's what happened. Positive, negative, and positive. So that means when you look at the integral, you have to split the integral at 3. So that means the total distance equal the integral of 1 to 4, the absolute value of vt. So why we do that? Because it's going to change the sign, it's become negative. So that means you have to split the integral into 2 parts. So we're going to go 1 to 3. In that part the integral is negative, so to get the absolute, that means to make it positive, you multiply by the negative sign, okay? And then plus, gonna go from 3 to 4. Here there is positive, so you don't need that, you just have vt dt. So that's exactly what happened here. So now you're gonna plug in and integrate. So we're gonna have 1 to 3 so negative, that means a negative t squared plus t plus 6. So we'll integrate that, plus you can integrate 3 to 4 where it is positive. So you have the same thing, t squared minus t minus 6, and integrate, and you can see that this is very easy to integrate. So this is negative t3 over 3 plus t squared over 2 plus 6t, and then 3 and a 1, plus here you have t3 over 3 minus t squared over 2 minus 6t. Here you have 4 and a 3, and if you simplify, you're gonna get 61 over 6. This is roughly equal to 10.17 meters. So during that time, even though the displacement was only 4.5, the particle moved 10.17 meters. Okay, so that's the difference. Okay, so please expect something like that in the next exam. So I will give you a similar question, and remember the steps. Those are not that difficult, but still there are certain things to understand. What happened when it is negative, what happened when it is positive. Okay, so I'm gonna also connect that. So it's negative, so you have to put the negative sign here just to make it positive, because you are looking for the absolute values. Okay, so thank you. So this is the end of indefinite integral part. Okay, so then we're gonna do the substitution method. That is one of the very important method. So please make sure that you go over these videos before you start the homework, because I'm gonna discuss some shortcuts that you cannot find them in the book. Okay, so thank you so much. Let's meet in the next video.